Dear students, let me explain important points regarding the chapter motion along a straight line. I'm going to start with the concept displacement. So in displacement, if the body moves in a circular path, and if r is the radius, and if the particle moves from point A to point B, describing an angle theta, then the displacement is given by the shortest distance. And that displacement here, in this case, AB is equal to 2r sine theta by 2. What is the distance covered? The distance covered is the arc length. So which is S is equal to r theta. Suppose if the particle moves from one point to another point, and with respect to the origin, I can measure a vector which is called position vector, r1. And that r1 can be given in terms of the unit vectors, which is x1 I cap plus y1 j cap plus z1 k cap. And if the particle moves from A to B, then for the new position, I can find another position vector, which is R2. So R2 is given by x2 I cap plus y2 j cap plus z2 k cap. So what is the displacement in this case? The displacement is from A to B. And that displacement from A to B, is given by vector r. And that vector r is equal to r2 minus r1. And that r2 minus r1, that gives x2 minus x1, I cap plus y2 minus y1 j cap plus z2 minus z1 into k cap. So that's the displacement vector. That's A to B. And how to find the magnitude of it? So you know, magnitude of any vector is given by a root of x2 minus x1 the square plus y2 minus y1 square plus z2 minus z1 the square. So these are the 3 points which you have to remember. Displacement when a body moves in the circular path. This gives the distance traveled when a body moves in the circular path. And then whenever a particle moves from one position to another position. So these are position vectors, whereas A to B gives the displacement vector. So let us learn about two important terms, that is the speed and velocity. The speed and the velocity. So when a body moves with the uniform velocity, the magnitude of the velocity is given by the ratio of the displacement by time. So keep in mind that if the body moves with uniform velocity, the ratio of the displacement to the time gives the uniform velocity. The average velocity is given by the difference in the position of the particle to the time taken. Suppose if it is given in terms of the vector, then r2 minus r1 gives the net displacement to the time and here we have the vector. So average velocity is the ratio of the total displacement to the total time taken. Instantaneous velocity. So how do we find the instantaneous velocity? Velocity of the body at a particular instant of time. And we measure it by finding the derivative of the displacement with respect to time. Sometimes they'll give a different variable. So it can be dx by dt, or it can be even dr by dt. So this is how we measure instantaneous velocity. So instantaneous velocity is the derivative of differentiation of s with respect to time gives the instantaneous velocity. So we have uniform velocity, average velocity, and instantaneous velocity. To find the uniform velocity, we use the total distance by total time taken, and for average velocity, the net displacement to the time taken for it, where r1 is the position of the particle in a time t1, and r2 is the position of the same particle at the instant time t2. So few special cases we are going to learn now. So let us consider a particle moves along a straight line with speed v1, v2, v3 in time t1, t2, t3, and so on. So what is the average velocity in this case? So v1, v2, v3 are the velocity of the particle at the instant of time t1, t2, t3, and so on. So what is the average velocity? So average velocity is given by the total distance covered. So let S1 be the distance covered or the displacement in a time t1. Then the net displacement is S1 plus S2 plus S3 and so on by the time taken, which is t1 plus t2 plus t3 and so on. But we can write this distance covered in terms of the velocity and the time. That is, v is equal to S1 is equal to v1 into t1, v1 t1 plus v2 t2 plus v3 t3 and so on by the total time taken, which is a t1 plus t2 plus t3. So this is how we can find the average velocity, or it can be even average speed, because when a body moves along a straight line, the average speed and the average velocity are same. Now, if the body moves along a straight line with the speed v1, v2, v3, and if it covers in equal intervals of time, if it is equal intervals of time, then t1 is equal to t2 is equal to t3 and so on. That I'm going to take it as a t. So in that case, v is given by, when t1, t2, t3 are same, we get v1 plus v2 plus v3 and so on by, and when t1, t2, t3 are identical, there are n terms are there, so divided by n. So we can use this equation only when, if a body covers or body moves along a straight line with the speed v1, v2, v3 in equal intervals of time. So this ratio, adding all the velocity divided by n is equivalent of the progression, arithmetic mean. Imagine if there are only two equal intervals. In such case, the n is a 2. And when n is 2, we get v is equal to v1 plus v2 by 2 for two equal intervals. If there are three equal intervals, then n is equal to 3. So we get average velocity to be equal to v1 plus v2 plus v3 divided by 3 and so on. So therefore, these equations are applicable only if a body moves along a straight line covering velocities or speeds of v1, v2, v3 in time intervals at t1, t2 and t3, then average velocity is given by these formulas. So these set of equations are very important. So let's learn one more special case. Where a body moves along a straight line covering distances s1, s2, s3 with the speed or velocity is a v2, v3, and so on. So what is the average velocity in this case, where the data that is given is the distances and the velocity. So the average velocity or average speed is given by, as usual, the total distance, which is s1 plus s2 plus s3, and so on again for n terms, divided by the time taken, which is the t1 plus t2 plus t3, and so on. But here the given data is the distances and the velocity. So therefore I have to replace the time in terms of s and v. So therefore v is equal to s1 plus s2 plus s3, so on, divided by this t1, which we can write in terms of, because we know that v is equal to s by t. So t is equal to s1 by v1 plus s2 by v2 plus s3 by v3, and so on. So this is the formula that gives the average velocity for a body covering distances s1, s2, s3 with the velocities the v1, v2, v3, and so on. Now, what if the body covers equal distances with the speed v1, v2, v3? In such cases, s1 is equal to s2 is equal to s3, and so on. So we get v is equal to, when s1, s2, s3 are equal, there are n terms are there, so we get n by this s. When they are equal, this will get cancelled with this s, thereby giving 1 by v1 plus 1 by v2 plus 1 by v3 plus 1 by v4, and there are n such terms. So this is a special case where we can find average velocity for n equal distances, n equal distance. And what is important is this equation is of the format harmonic mean. It's a harmonic progression, out of which we can again take special cases. If there are two equal distances, then we get v is equal to 2 by 1 by v1 plus 1 by v2. And on simplifying, we get v is equal to 2v1 v2 by v1 plus v2. That is for two equal distances. What if a body covers certain distance with the three equal distances? The total distance split it into three equal parts, okay, or three equal distances. In that case, we get v is equal to 3 by 1 by v1 plus 1 by v2 plus 1 by v3, and that gives v is equal to, it's 3 v1 v2 v3 by v1 into v2 plus v2 into v3 plus v3 into v1. So this is for three equal distances. And in NEET, you get to see problems where they combine the previous case as well as this case. Okay, where they'll give a body covers the first two half with the equal intervals, and then the rest of the half is covered with equal distances, in which case we have to combine the two cases that we have discussed just now. So let's learn something about an important term, which is acceleration. A body is said to have acceleration whenever there is a change in velocity. That can be either in magnitude or in direction or in both. And our acceleration is given by dv by dt. That is rate of change of velocity. I can use this to find the instantaneous value. Instantaneous acceleration. But sometimes this acceleration is a function of distance or displacement. In that case, you cannot use this. You can use this equation only if velocity is a function of time. What if v is given as x 2x plus 3x squared, where v is not a function of time, it's a function of distance. In that case, you can find the acceleration is equal to v into dv by dx. So we use the first format only if v is a function of time, and we use the second format if v is a function of distance or displacement. And in terms of the distance, it is double derivative, which is d square x by dt square. Suppose if the body moves with the uniform acceleration, and if you know the initial and final velocity, you can even use it as v minus u by t. So I've combined all the equation in one. So acceleration is a derivative of the velocity if velocity is given, and we use the same formula to find the acceleration if v is a function of x, and if only x is given, differentiate that twice, double derivative, and if you know the initial and the final velocity, we can use the change in the velocity with respect to time. Now, how to find the average value? The average value is the change in the velocity, the net, which is in terms of the vector, divided by the time taken for it, where v2 is the velocity of the body at an instant t2, and v1 is the velocity of the body at an instant t1. So this is how we can find the acceleration of a body. Next, we have an important concept that when a body moves with uniform acceleration, a body moves with uniform acceleration, what is the relation between the various physical quantities? So which we have derived in the form of equations of motion. So to find the velocity at an instant, we use the format v is equal to u plus at. So this will give you the velocity at an instant t. So to find the displacement in a given time, we use s is equal to ut plus half at square. The same thing can be even found using vt minus half at square. If I replace the u as a v minus at, then we are going to get this particular format. And the same distance we can even calculate as u plus v by 2 into t. So s is equal to ut plus half at square, vt minus half at square, u plus v by 2 into t. So this is the average value. Now, advantage of this particular equation is that we don't have to use the quantity acceleration. Check this here. We have used acceleration here. We have used acceleration. So this is the only equation where we don't use the acceleration term. So that's why to avoid calculating acceleration, we go for that last format. S is equal to u plus v by 2 into t. Then velocity after completing or after covering a certain displacement s is given by v square is equal to u square plus 2as. So we have two more special cases. That is to find the displacement or distance during nth second. That is Sn is equal to u plus a into n minus half. That is same as u plus a by 2 into 2n minus 1. And then we have one more special case where if a body covers two distances, s1 and s2, in equal intervals of time, then the acceleration is given by s2 minus s1 by t square. So most of the numericals are based on these 5 equations, and the condition to use this equation is that we have to make use of the uniform acceleration. Suppose if an equation is given where v is equal to root of s plus 121, let's consider. Okay. Now in this case, what is the acceleration? How to find the acceleration? So v is equal to square root of s plus 121. If you want to find the acceleration, now one of the equation, now you can see here v is not a function of time, v is a function of s. So one of the equations which are given to find the acceleration, a is equal to v into dv by ds. So that will give you the value of the acceleration. But here, this will take more time in finding the acceleration. So if you look at this particular equation, this equation is of the format. If I square it, I'm going to get v square is equal to s plus 121. It's also v square is equal to, so this is u square plus 2as. So what you get to notice here is a u square is 121. So with which I can find the value of u, which is 11. And the value of 2a is 1 here, because 2as, the value of 2a is 1. So that will give you 8.5. So we can more easily find the value of the acceleration using this equation rather than differentiating, because that takes more time. So that's why always compare whether the given equation is of the any of this particular format. If the given equation is of this format, then definitely the acceleration is uniform, and with which we can find the value of the acceleration more easily. Suppose if I give a slightly different equation, where if I give v is equal to root of s square plus 121. By looking at that equation, we can make out that it is not of any of this particular format. That means the acceleration is not uniform. In that case, we have to make use of this format of the equation, where the value of a is there, so you can differentiate, use the value of v, and then you can find the acceleration. So therefore, always compare whether the given equation is related to any of this equation. In that case, directly we can find the value of the acceleration more easily rather than differentiating, because the differentiation will always takes more time. So these are the equations of motion. Now, when velocity is given, v is equal to ds by dt, and if you want to find the distance, correct, then we have to always integrate. So therefore, rearrange ds is equal to v into dt, and then on integrating, we'll get s here is equal to integration of v dt. And if you know the initial velocity and the final velocity, you can always use the limits here, v1, v2, and moment you use the limits, the integration constant is always 0. So we don't get an integration constant, so that you can find the value of s. Similarly, a is equal to dv by dt. Whenever acceleration is given, and if you want to find the velocity, integrate it, dv is equal to a dt. So here again we get the velocity, and then if you know the time interval, you can always write t1, t2, and then we can find the value of, so this is sorry, in terms of the time here, but it's a function of time, t1, t2, and then we can find the velocity. So the differentiation and the integration are the important tools which is used to find the velocity or the acceleration. So let's consider a situation where when a bullet is fired with a velocity u. And a bullet is fired with a velocity u, and if it penetrates a block, and if it penetrates through a distance s, so use the velocity, and s is the distance. And after penetrating, it comes to rest. So in such case, we can always use what we call, and this s is called the stopping distance. So stopping distance is always directly proportional to square of the initial velocity. Now, how do we get this particular equation or the relation? And then there are questions where they'll give, if the stopping distance is double, what is the distance covered? If the stopping distance is double, the stopping, if the initial velocity is double, the stopping distance increases 4 times. Because here u, when you write this as 2u the whole square, this factor increases 4 times. If the stopping distance is half, if the initial velocity is half, then the stopping distance decreases 4 times. And we get this particular equation using v square is equal to u square plus 2s. Here the final velocity of the bullet is 0. Initial velocity is u square is equal to 2s and u square is equal to minus 2s. And for a block, this minus 2a is a constant, and that's how we get s proportional to u square. So it's a special case which you need to remember for the numericals, where they'll ask the initial velocities of the bullet will be given, and then you have to relate that to the stopping distance. Okay, so where final velocity is 0, and we cannot use this equation suppose if the bullet emerges out of the block, because in that case the final velocity is not 0. So this is applicable only when it penetrates the block through a certain distance, or where s can be even considered as the thickness of the block. So now let us use this equations of motion for a body which is moving under the action of gravity. So when a body falls due to the gravity, we can always use v is equal to u plus g into t, where a is equal to plus g for freely falling body, and when a body is thrown vertically upward, the value of a is taken as minus g. So therefore I'm going to write plus or minus g. But for free fall, u is equal to 0, whereas when a body is thrown upward, the final velocity becomes 0. So accordingly we can modify this equation. Then s is equal to h, where h stands for the height from which the body is dropped, and if this is the surface of the ground, then h is equal to ut plus or minus half g e square. V square is equal to u square plus or minus 2gh. V square is u square plus or minus 2gh. Sn, or I can even write hn, is equal to u plus or minus g into n minus half, and then plus or minus g is equal to h2 minus h1 by t square. All those equations of motion which are given now can be used for a body falling freely or when it is thrown upward. But as I've mentioned, when a body falls freely, when u is 0, we can always avoid this, and then we can write v is equal to gt. So straight away we can use such formulas to solve a lot of numericals in the case of body either falling freely or thrown upward. So v is equal to gt, or you can even write t is equal to v by g. So what about for a body which is thrown upward? The format is the same, which is u is equal to gt. In this case, v is the final velocity with which the body reaches the ground. This is the initial velocity with which the bodies are thrown upward, or t is equal to u by g. So when we replace here, h is equal to u is 0, so we get h is equal to half g t square. So h is directly proportional to the square of the time taken, or we can even write t is equal to 2h by g with the root. So same is valid even in the case of body which is thrown upward. The same formats can be used. And then finally, in this case, v square is equal to u square plus 2gh, where u becomes 0. In that case, v is equal to, or v square is equal to 2gh, or v is equal to root of 2gh. Root of 2gh. So how about h in this case? H is equal to v square by 2g. And when we use the other set of equation for a body which is thrown upward, we get u is equal to root of 2gh, or even h is equal to u square by 2g. And that very clearly shows that when a body is thrown upward, the velocity with which it is projected is equal to always the velocity with which it reaches the point of projection. Velocity with which it is projected, u, is equal to the velocity with which it reaches the point of projection. And that is the reason why the time taken by the body to reach the maximum height is equal to the time taken to come back to the same point. That is, time of ascent is equal to the time of descent, with the assumption that there is no air resistance. In the presence of the air resistance, time of ascent is lesser than the time of descent, because during upward motion there is a less resistive force, whereas during downward motion there is more resistive force because the velocity continuously increases. So the viscous force or the air resistance continuously increases. That's why it takes more time. So that's why time of ascent is always lesser than the time of descent in the presence of the air resistance. Otherwise they are always equal. So in these cases, you have to remember with the various relation, like h directly proportional to t square. So that means when t is doubled here, h increases 4 times. In this case, when h is a double, t increases root 2 times. So same thing here, if h is a double, v increases root 2 times because it's within the root. Here, if v is a double, then h increases 4 times. So such proportionality is very useful in these equations related to the motion under gravity. So a few special cases under this I would like to explain. That is, consider a tower having height h, and if a body is thrown upward with a velocity u, it reaches the certain height, which I'm going to write. So let this capital H be the height of the tower, and its small h be the height above the tower. So it reaches certain maximum height, and then as it falls, I'm going to assume that it's going to reach the ground. So when it's thrown upward with an velocity u, it comes back to the same point from the point where it is projected with the same velocity but in opposite direction. So that's why this velocity at this instant is taken as minus u. And when it reaches this point, what is the net displacement? The net displacement is 0 because it reaches the same point of projection. So that on reaching the ground, the net displacement is same as the height of the tower, but with an initial velocity u. So therefore, in this type of problem, the net displacement, which is h, is equal to initial velocity minus u t plus because it's moving in the downward direction. So that's why we write it as half gt squared. So again, this equation is exclusively used for a body thrown from the top of the tower in the upward direction with a velocity u, and t, keep in mind, is the total time taken by the body to reach from the initial position till the ground. So t is the total time taken. What is the velocity with which it reaches the ground? That can be calculated using v is equal to the initial velocity is minus, and then the time taken, that's a u plus g into t. So this is the equation with which you can find the final velocity with which it reaches the ground. Now, the same equations are applicable for another situation where, so we have a ground, and then at a certain height, which I'm going to consider as h, at a certain height. So there is a so there is a hot air balloon. A hot air balloon has reached an height h from the ground. And from that balloon, if a body is dropped from the hot air balloon, if a body is dropped, let us consider at this instant, let u be the velocity of the hot air balloon, which is ascending. If u is the velocity, h is the height above the ground, and from that, if a stone is dropped. Now, because of the velocity of the balloon, the stone will move in the upward direction and then it will fall back. even though the stone is dropped, because of the velocity of the balloon, it will continue to move upward with to a certain height, and then it will fall back. So what is the net displacement in this case? The net displacement is height of the balloon above the ground, which is h. Then, since it moves upward and then it falls back, when it reaches here, its velocity is minus u in the downward direction. That's why it is minus ut plus half gt squared. So it is the same formula which we'll be using it. And again, velocity with which that stone reaches the ground is given by v is equal to minus u plus gt. So then what is the difference? In this case, what is h? H is the height of the tower. In this case, what is h? It is the height of the balloon above the ground. Here, what is u? Velocity with which the stone is thrown upward. And what's the t? Total time taken by it. Here, what is u? Here, u is the velocity of the balloon at the instant when the stone is dropped. And what is t? The same thing, total time taken by this. So therefore, we use the same set of equation in both the cases. Only difference is, in the first case, the stone is thrown from the top of the chart. And in this case, the stone is dropped from certain height. So two cases, identical formats of the equation, and definitely it's an important concept for the exam. So one more special case I would like to explain. So we have a tower of height h, from which the body is thrown upward, and then it reaches certain height, and then it falls back. And it takes time t1. And we can write the value of height, h is equal to minus u t1 plus half g t1 square. Now from the same tower, another stone is thrown downward with the velocity u. It's a thrown downward, not left free to fall, thrown downward with an velocity u, covering the same height. Let us take it takes a time t2. So then I can write h is equal to, it's a thrown with a velocity u, time taken is a t2 plus half g t2 square. And in the third case, if the same stone is a drop, that's u0, and then it takes time t3. So it's thrown here with a velocity u. Here it's a thrown downward with the same velocity, and then later it is allowed to fall free. And in this case, the equation for h is equal to u is 0. So I'm going to get half g t3 square. And now the relation by solving this equation, we can find the relation between t1, t2, and t3. That is, t3 is equal to root of t1, t2. You can even find the height. H is given by half g t3 square. T3 is this. So square of it will give you t1. By substituting the value of h here, you can even find the initial velocity. It was given by u is equal to half g t2 minus t1. It's a t1 minus t2. So these are the three equations that can be used again only in this special case. So some of the special cases, if you remember, so many problems again can be solved very easily. Any problem relevant to this can be solved very easily in NEET exams. So one more special case again I'd like to explain, that is the body is thrown from the ground with an velocity u. It reaches a certain height h, but it covers a maximum height which is capital H. So time taken to reach this height h in upward direction I'm going to write it as T1. Again, it moves further and it goes upward, covers maximum height h, and again it falls back to the same height. By then, it takes a total time of T2. So that means the particle will be at the same height at two intervals of time. One is a T1 and the other is a T2. In that case, the velocity with which it is projected is given by half g into T1 plus T2. So initial velocity with which the body projected so that it reaches the same height at two different intervals is given by u is equal to half g into T1 plus T2. Again, numericals have appeared in the NEET exam based on this concept. So let me explain another important concept, which is relative velocity. So we use the relative velocity whenever two bodies are moving simultaneously in different direction. But in this chapter, we are going to restrict our explanation only for bodies moving along a straight line. If two bodies are moving along a straight line, but the velocity is v1 and v2. So what is the relative velocity of one with respect to other? What do you mean by relative velocity? Relative velocity means velocity of one body as appears to the other. So that is v1, 2. So velocity of the first body with respect to the second is always given by the difference when they move along the straight line. So v1 minus. And if you want to find v21, then it is a v2 minus v2. So the velocity, relative velocity, is always the difference if the two bodies are moving along the same direction. Now, what if they move in opposite direction? If this is v1, with respect to the first body, the direction of the other is it's a minus. So therefore, in that case, we find v12 is equal to v1 minus of minus v2, which is v1 plus v2. That means the relative velocity is lesser when the two bodies move in the same direction, and the relative velocity is more when they move in opposite direction. So how about v21? So v21 is equal to v2, which is minus v2 here, minus of, again here v1, which is minus of v1 plus v2. So that is the relative velocity of one body with respect to another. So find the difference in the two bodies when they move in same direction, and add the two velocity when they move in opposite direction. And we can make use of this concept whenever two bodies move simultaneously. So for example, here if they give a body A moves with an uniform velocity v, and if there is one more body moving with an acceleration a having initial velocity u, and if the separation between them is s. So what is the time taken by the first body in overtaking the second? So one of the method is write two independent equation and then try to relate them. The other easy method is, if s is the distance to be covered between A and B, then s is equal to u relative. What is u relative? Here, its initial velocity is a u. Here, I'm going to assume that it's going to start from rest, or if v is the uniform velocity, then the relative velocity between them is a v minus u. So that's the relative velocity between the two, v minus u, into t, that is s is equal to ut, plus half, there's no relative acceleration between them, because this moves with uniform velocity. Therefore, the relative acceleration is a minus 0, which is a, and then t square. So therefore, if you know the value of s and if you know the value of acceleration, so you will get an quadratic equation, and you can find the time taken by the body A to cover or to overtake body B. So always use the relative velocities, and then you use one equation to solve this entire numerical rather than writing two independent equations, which takes a lot of Right. And based on this relative concept of relative velocities, we have a few equations to be remembered. So let's take, so there is a boy, and then there is an escalator. So first, the boy is going to walk on a stationary escalator, and it takes time t1 to reach the next floor. In the second case, the boy is going to remain at rest in a moving escalator, and it takes him in a time t2. And what if the boy walks on a moving escalator, and if it takes a time t, then t is given by 2t1 t2 by t1 plus t2. So we get this formula by using the relative velocity. You can see we use the relative velocity here because both the boy and the escalator is moving. So we arrive at a relation t is equal to t1 plus t2 by t1 plus t2. Let me repeat here. So in the first case, the boy walks on a stationary escalator, and he takes time t1 to reach the floor. And then in the next case, the boy is going to stand on a moving escalator. It takes time t2 to cover that same distance. And now if the boy starts walking on a moving escalator, and if it takes time t, then t is equal to 2 into t1 t2 by t1 plus t2. So this is again another important equation based on the relative velocity. So one more similar equation I would like to give, that so there is a motorboat moves with the velocity v1 down the stream. So there is a river flowing in the direction, and in this case, the motorboat, to cover a certain distance, it takes time t1. So when the motorboat, let me write VB here, and the motorboat moves in the direction, in the downstream of a river flowing with a velocity VR, it takes time t1. If the same motorboat, if it moves upstream in the same river, then it takes time t2. Then what is the time taken by the motorboat, correct, in still water, still not a flowing water, in still water. So here also we are going to use, see here we are going to find the difference in the velocity because the boat and the river are in the same direction. Here we're going to add the two velocities, and here we have only one velocity because there's no velocity to the water, and by using that we get t is equal to t1 t2 by t1 plus t. So this is another special case which is used based on the concept of relative velocity. So using the same concept of relative velocity, so one more equation, that is, if a body is dropped from a certain height h, and if one more body is thrown upward with a velocity u, then the time after which the two bodies meet, t, is given by its g by u. So time after which the two bodies meet covering a distance h is given by t is equal to g by u, where u is the velocity with which the second body is thrown upward, because the first body is dropped freely from certain height. So one more important concept here in this particular chapter is the graph. So we have three types of the graph, which is xt graph, vt graph, and the at graph. So before explaining, I would like to give some introduction to the graph, the basics of the graph. Now, when we draw a graph, so there will be two variables, one which is taken along the y-axis, the other is taken along the x-axis. And if the graph is a straight line passing through the origin, then that particular graph should be of the format y is equal to mx, where m is the slope of this particular graph. And we can always compare this equation with that of the equation that we come across in physics, and then we can understand what is the nature of the graph. So for example, if I write this equation is of the format s is equal to v into t. S is equal to v into t. So s is taken along the y-axis, t is taken along the x-axis, which is a st graph, and you can see slope gives a velocity. So therefore here, slope of st graph gives a velocity, which we also call it as a xt graph. So therefore, to understand the graph, first compare the equation pertaining to the graph with that of the equation that we come across in physics. It's very easy to draw the graph. So I'm going to draw one more graph here, and the same. That is a graph where the y-intercept is a negative and the slope is positive. The slope is also given by tan theta. So that means if you know this angle, if this angle is 45 degrees, then we can find the slope to be equal to 1 because tan 45 is 1. If this angle is 60 degrees, then the slope is equal to root 3. Tan 60 is equal to root 3. So we can find the slope very easily. But the y-intercept here is a negative. So this equation is of the format y is equal to mx minus c. The slope is positive, whereas the y-intercept is negative. So the third case which I'm going to draw here is this, where y is equal to, slope is positive, this is a slope, positive, mx plus, even this slope as well as the y-intercept is a positive. Now, for this equation, I can write v is equal to ut plus, v is equal to u plus 8. Okay, v is equal to, let me write here, u plus 8. So that's equation y is equal to mx plus c. So where along the y-axis, the velocity is taken. Along the x-axis, the time is taken. So which means basically it's a VT graph. So the slope of the VT graph gives the acceleration. Very easily you can compare here. Whereas the y-intercept gives the initial velocity. So this is called a linear graph or the straight line. So therefore, the straight line can be passing through the origin. It can be a straight line with the negative intercept, or it can be with the positive intercept. So these are the different kind of graph that we come across in the various chapters, and this is a way to identify the nature of the graph. So one more set of graph which I would like to draw here is a linear graph, but with a negative slope. So this is one of the straight line. This is the other, and this is the next. So in this case, you can see the slope m is equal to tan theta. So when theta is obtuse, m is a negative. So that's how we get negative slope. Whereas the intercept here, y-intercept is positive. So therefore we get this equation, or the equation for this straight line is y is equal to minus mx plus c. So for this, y is equal to, slope is negative, minus m, it's a x, c0. There's an equation in physics, F is equal to minus kx. The restoring force or spring force is equal to minus kx, where k is a spring constant or force constant. So the equation for F versus x is a straight line passing to the origin, and it's in the second and the fourth quadrant. So this is the graph for f is equal to minus kx. And the last, y is equal to minus mx and minus c, the graph. So normally we don't have any such graph as such in physics, but for the rest of the straight line, so there are equations where we can always compare the equation of the straight line with that of the equation that we come across in the various concepts. Okay? So any equation of this format is definitely a linear one. So for example, we have the charge is stored, Q is equal to CV. So if I have to draw a graph of Q versus V, then this y is equal to mx. So Q versus V is a straight line passing through the origin, and the slope is the capacity of the capacitor. If it is V is equal to Ri, the Ohm's law. So again, it's y is equal to mx. So V versus I is a straight line with the slope equal to the resistance. So this is how one can identify the nature of the graph with these formats. The other set of the graph is where it's not a linear one. So we get equations of the format y is equal to x squared. When x is 0, y is 0, which is the origin. And now when x is positive, y is also positive. So let's consider somewhere here. When x is negative, y is positive, just here. So here we have 3 points. And when you draw them, you'll get a parabola. So any equation is of the format y is equal to x squared is a parabola through the origin and symmetric about the y-axis. And we have plenty of such equations in physics. So kinetic energy K is equal to half m v squared. So here K versus V is a parabola through the origin, and it's of this format. So we have power P is equal to I square into R. So we have U is equal to half CV square. So these are all examples for y is equal to x square, which is a parabola through the origin. The other formats of the equation is y square is equal to x, where when y is 0, x is 0, which is the origin, and when y is positive, x is positive. When y is positive, x is positive. When y is negative, square, so x becomes a positive, which is here. So this time again it's a parabola, but symmetric about x-axis. So the equation for such is v square is equal to 2as. So therefore, v versus s is a parabola symmetric about the x-axis. V versus s. Or we have an equation for velocity of sound. V is equal to root of gamma RT by m. And when I square it, I'll get v square is equal to gamma RT by m. So here, velocity of the sound versus temperature is of the format y square is equal to x. So therefore, it's a parabola, again symmetric about the x-axis. So compare the equation of the parabola or the straight line with that of the equation, so you can understand the nature of the graph very, very easily. So we have learned parabola, we have learned straight line. Suppose if the equation is of the format x square by a square plus y square by b square is equal to 1, then it is an ellipse. And then if a is equal to b, if a is equal to b, then the x versus y or y versus x becomes a circle. Okay, and we do have the graph example in the case of simple harmonic motion. Velocity versus displacement is a ellipse with a and b. So b is the minor axis, semi-minor axis value, and b is the semi-major axis value. So that is the various shapes of the graph. Now, in the case of VT graph, velocity versus time. So you have to remember the various cases so that very easily you can identify the nature of motion. Suppose if the graph is a straight line parallel to the time axis, there's no change in velocity. So the nature of the motion, the body moves with uniform velocity. VT graph, the slope of the VT graphs always gives acceleration. V is equal to U plus AT. Y is equal to mx plus c. So if you know the angle, you can always find the acceleration. A is equal to tan theta, that's equal to m. Initial velocity is 0. The body moves with uniform acceleration. The slope m is negative. That means A is negative. A negative means it's a retardation. So the body having certain initial velocity moves under a uniform retardation, which is A is a negative. Uniform velocity, uniform acceleration with the zero initial velocity, and this is uniform retardation. And then if I draw a graph like this, the body has certain initial velocity and then again moves with the uniform acceleration. So these are the various cases that we come across in a graph which is called VT graph. The case of position time graph, XT graph. Position time graph, XT graph. Here, as the time changes, time increases, there is no change in the position. That means the body is at rest. There is a continuous change in the position with a constant slope. How to find the slope of any graph? The slope is equal to the change in the y-axis to the corresponding change in the x-axis. So the change in the y-axis is nothing but dx. The corresponding change in the y-axis is nothing but dt. So dx by dt gives a velocity. So therefore, the slope of the xt graph gives always the instantaneous velocity. And then, if there is a continuous change in the slope, then s is equal to half at square, or x is equal to half at square. So therefore, this is of the format y is equal to mx, y is equal to ax square format, y is equal to ax square format. So therefore, we get a parabola where you can see the slope here, the angle continuously increases. That theta continuously increases. What do you mean by increase in slope? Increase in slope means increase in velocity. And when the velocity increases, there is acceleration. So therefore, we get a parabola whenever body has a uniform acceleration. And if a body moves with uniform retardation, again we get a parabola, but with a decreasing slope. So again, you can see here, the slope continuously decreases. That means the body has uniform retardation. So we get parabola only when body has uniform acceleration or uniform retardation. So this is the two types of the graphs which is very important. One is xt graph and the other is VT graph. Now let us draw xt graph, VT graph and then AT graph for a body which is thrown upward. So let's take a body which is thrown upward. Acceleration is negative, which is minus g. And then it reaches a certain height and then it falls back, during which the acceleration is positive, plus g. So for this entire journey from point A and then back to the same point, which I'll write it as B, What is the xt graph? What is the vt graph that we can draw? Xt graph. When a body is thrown upward, the body has retardation, and I've told you that when it is retardation, the kind of the graph that we get is a parabola. Is a parabola. Now, relative to this, when the acceleration is positive, you're going to get the inverted parabola like this. From this, we can understand the nature of motion. Point one, when the body reaches the highest position and when it reaches the maximum height, its velocity is 0. And that we get to see here. The graph becomes parallel to the time axis. That means what is the slope here? The slope is 0. When the slope is 0, the velocity is 0 because the slope of the xt graph gives the velocity. Not only that, while moving upward and then downward, the particle crosses the same position twice. So that's what we get noticed here. You can see while traveling upward and downward, it crosses the same position twice. So that is the reason why it's the graph of xt. Graph of xt for a body which is thrown upward and then it falls back is a complete parabola like this. So how about vt graph? When it's thrown upward, acceleration is negative. So that means the slope of the vt graph is negative. So therefore it's a straight line with a negative slope. And then when it reaches the highest position or maximum height, its velocity becomes 0. And then when it falls back, its acceleration is positive. So therefore this straight line becomes, again, it will continue to remain a straight line, but it will be in the next quadrant. Why it is in the next quadrant? The reason that at a particular instant, if u is its velocity, and then when it comes back to the same position, its velocity will be minus u. It's in the value of the velocity is the same, but it's in the negative direction, opposite direction. That's what we get to notice, that if its velocity is positive during the upward motion, during downward motion, its values are negative. So that's why the graph will be in the next quadrant. So where if this is plus v, this will be minus v. What about speed versus time graph? So this is a velocity versus time graph. If it is speed versus time graph, the first half, it's the same. It's a vt graph straight line with a negative slope. But during downward motion, magnitude of the speed remains the same. Speed cannot be negative. So therefore, again, it's a straight line with the positive slope. Initially, it's a straight line with a negative slope, and now it's a straight line with a positive slope. And again, you get to see that it will attain same values for a particular height, and speed cannot be negative. So therefore, the difference between this graph and this graph is that, so here this is a velocity versus time graph, is a straight line, and here it's a speed versus time graph. And the last is acceleration versus time graph, AT graph. For upward motion, A is negative, so therefore it's a straight line, and again it's a constant, so it's a parallel to the time axis. A is negative, and then A becomes a positive, again it's a constant, so therefore again it's a parallel, but in the positive quadrant, or in the first quadrant, A is positive and here A is negative. So therefore these are 4 graphs. That's xt graph, and then the vt graph. Speed, this is velocity versus time graph, this is speed versus time graph, and this is acceleration versus time graph for a body thrown upward and then it falls back to the same point. So students have explained all the important concept of motion along a straight line, and revise all these equations, and then attempt as many questions as possible. So before you attempt more and more questions, correct, first make sure that you revise these equations and then go for attempting more and more questions. So in the next sessions, I'll be explaining one more concept. So till then, take care, and then solve as many questions as possible from motion along a